Gravitational waves are unique in the sense that they carry information about violent cataclysmic events, astrophysical events that you can't get from any other way. So optical telescopes, radio telescopes cannot reveal the kinds of things that we can see, or in the analogy we use is hear, with gravitational waves. So it's really a unique way to look at some of the most violent, some of the most cataclysmic events in the universe. Even the Big Bang could be only seen through gravitational waves. I think it is a revolution. The question is how revolutionary, and I think the next 10 to 20 years will tell us how revolutionary it is. We should be seeing things with gravitational waves that you can't see any other way. And every time you develop a new kind of astronomical technique, astronomical telescopes, radio telescopes, you discover things that you could never have anticipated. And so I think in the next 20 years, we may see things that we just couldn't even conceive of, and that will shake what I would call the scientific paradigms of the day. We may even learn, for example, that Einstein's theory of relativity is only an approximation to something better. It could lead to a new theory of gravity that incorporates quantum mechanics. Only time will tell, but I'm very excited. I think it's going to be very exciting over the next 20 years. I would love to see two things happen. I would love to see the first hints that general relativity is wrong, and we can get that information. We measure waves, these gravitational waves, directly with our interferometers. They're direct measurements of ripples in space-time. And if general relativity is wrong, the way those waves propagate will encode themselves on our interferometers. So we'll be able to see that perhaps Einstein didn't get it quite right. I think that's very exciting. There may be clues to other sorts of things. For example, the nature of dark matter. People have even postulated after our discoveries that these black holes that we saw were primordial black holes and may make up a fraction of dark matter. I don't believe that yet because we have to have enough data, but we may be able to tell that in the future that we're actually seeing dark matter. So that could be very exciting too. I think it'd be a combination of satisfaction that his theory was right. Right? Of course, Einstein had a lot of confidence in himself, so he may not be totally surprised by this. I think he'd also be amazed, because I think when he started thinking about gravitational waves, when the theory predicted the gravitational waves, in his paper he himself said they're of little practical consequence. And the reason they're of little practical consequence is because the size of the effect, the size of the waves, the amplitude is so tiny. There was no hope in Einstein's time of seeing these things and measuring them. But now we have the technology to be able to do it. So I think he'd be amazed, not only that we saw them, but at the technology also. So I think he'd be really excited. Probably not surprised, because again, he predicted them, so it was just more evidence that Einstein was right. Yeah, I don't believe that we'll be able to use gravitational waves to get to time travel, but perhaps I'm wrong. I mean, my imagination can only go so far. But I do think black holes are unique in the sense that they're really the only place in the current universe that we live in, or how far we look back with our telescopes, that we can look at gravity in a completely new way. So right around the event horizon of a black hole, that's the black part where if you go beyond the event horizon, you can't get out, you're trapped. There may be some funny things going on that relates to more quantum theories of gravity. And by looking at how event horizons evolve as they collide together, we may be able to see something interesting that points away towards a new theory of gravity that goes even beyond general relativity. And I think that could be very, very exciting. Might we see wormholes? We might, but that's again I think at this point speculative. But I come back to the fact that you never know what you're going to see until you see it, and when you see it, you'll be amazed. Spain, there's a group at the University of Balearic Islands that has played a key role in some of the searches that we do for gravitational waves. Now they're looking for a different kind of gravitational wave source. It's not black holes like we discovered last year. They're looking for gravitational waves from neutron stars that are spinning around. And these might produce gravitational waves if there's some mountain or something on the neutron star, but they're very, very tiny. And so what Professor Alyssa Sintes has done is she's developed some very powerful techniques for looking at the data that comes off our detectors to be able to search for these gravitational waves. Now, I think we're still a long way off from seeing them, but it's possible in the next few years that we might be able to see them. And I think that would be very exciting. And if that happens, and when it happens, I think Professor Sintes will be able to take a lot of credit for developing the techniques that we use to find those gravitational waves. Science is at the forefront, fundamental basic science, be it physics, chemistry, astronomy, mathematics. It's at the forefront of everything we do technologically. So if you think back 100 years ago, all right, we didn't know quantum mechanics existed then. It came along, and when the theory of quantum mechanics came along, it was a theory that was supposed to just think about how atoms behave, how subatomic particles behave, all right? Without quantum mechanics, we wouldn't have computers, we wouldn't have iPhones, we wouldn't have televisions, we wouldn't have a lot of different things. So fundamental research, and even LIGO has produced some technological things that are quite interesting. Fundamental research is at the beginning of every kind of technology that we have. So I think it's very important. You know, in a time of budget austerity, it's easy to say, let's cut back on the fundamental research. But what you do when you do that is you basically shortchange the future. You're basically selling the future just to satisfy short-term requirements. So I think it's a mistake, and I think most scientists would tell you that it's a mistake. The other thing I'll say is that's very important. One of the best benefits of the kinds of research we do is the people that get trained. So if you think about the people that have worked on LIGO, including some of Professor Sintes' students. These are students that are trained to do very fundamental things in physics, but they're trained to think in a certain way, and they can take that knowledge and go, and instead of working on some physics project, they can work on some engineering project or some computer project. So a lot of the knowledge that we give our students by helping them search for gravitational waves, they carry and go into industry, and I think that's quite exciting. So I think there's a lot of benefit that maybe the public doesn't understand that comes from funding fundamental research, but that's critically important for future economic development. Yes, so everybody asks what's the benefit of LIGO, and fundamentally the benefit of LIGO is we are understanding the universe at a completely new level, in a completely new way. And that in itself is very exciting, and you can't discount how important it is to push the boundaries of human knowledge. Once we stop pushing the boundaries of human knowledge, we give up some fundamental part of our reason for being, and I think that would be very sad. I would like to think so. Theories that, as we know them today, tell us that LIGO as a detector is unlikely to see gravitational waves from the Big Bang, from the primordial universe. There are other detectors that are under development that will be able to do that, right? Gravitational waves, like electromagnetic waves, come in a spectrum, so different wavelengths, and LIGO looks at very short wavelengths, very high frequencies. The Big Bang, these wavelengths are the wavelengths of the entire universe. Basically, they're as big as the entire universe. So the fact that we won't see them doesn't mean that LIGO isn't interesting. It just means we're looking at a different spectrum. The fact that I hope they'll be seen in the next 5 to 10 years, that's going to tell us something about the nature of the universe. And again, it comes back to the fact that fundamental knowledge just is so important to the way we live our lives as human beings. I think you actually said it well yourself. I've thought about this a lot because I was amazed at the reaction, the general public reaction to our discovery. It showed up on most major newspapers. Even in the last year, there's still some excitement about this, even though the result's a year old. I think there are a number of things that play in here. First of all, it's Einstein. Einstein is always very exciting. The discovery came 100 years after his theory of general relativity. That's very exciting. The fact that it took 100 years from the time the theory was predicted, or the phenomenon was predicted, till the time we saw our first gravitational wave. That's a story, and it took 50 years from the time we actually started building instruments to try and detect them. That's a story of human curiosity, of the ability of human beings to do very difficult things and take the long view of basically saying this is something important. It's tenacity at its best, and I think that's exciting. What we saw was interesting. Black holes are always fascinating. The public loves black holes. I love black holes. I think that's exciting. The fact that our detectors measured a signal from these two big, massive black holes colliding that was a tiny, tiny fraction the diameter of a proton, all right, that's phenomenal too. I mean, there's just a lot of out there science in this, and there's a great human interest story. Teamwork is another one. It took 1,000 people, over 1,000 people, to do these kinds of measurements, to build the detectors, to analyze the data. So there's a collaborative spirit that exists here. So you put all that together, all that in the mix, and you've got a great story, a great scientific story, a great human interest story. It's all there. I respect them for doing whatever they want. The Nobel Committee, the prize is set up in such a way that, of course, it awards no more than 3 people the prize. And for LIGO, that's a difficult thing to do because so many people have made such a deep contribution to this that it would be hard for me to point out 3 people. So I hope, if it's possible for the Nobel Committee to realize that it's the entire collaboration that made this discovery. Whether or not their rules will allow for the entire collaboration to get the prize, I don't know, but I would hope that they do. In any event, whatever the Nobel Committee does, that's what they will do, and I will be happy with it.